Hey, what is going on, everyone? Here we are from our studio. That's kind of funny. But anyways, we are changing what we're going to do here today. We have the Titanic Survival data. It's already locked and loaded. So this is what we're going to do with this. This is very exciting because everybody knows the Titanic. And some people survived. And that's what we're going to see today. But notice something about this. We are changing to the GLM, General Linear Model function. Why? Well, let's think about it. We're going to have, instead of continuous dependent variables, we're going to have both dichotomous, independent and dependent variables. So we have to change things up, and we're going to have to read it differently. So this is going to be very exciting. So let's take a look at this. So the GLM function works similar to the others, right? You do GLM, here it is. And then we want to know what's the dependent variable is survived. So we put in survived. And then we put in Antia. And then we are going to put in sex. And we also need family equals binomial. This is the regular distribution, the Gaussian distribution, binomial, which we're going to use here. And we have to actually write it. And because I've been playing around with a few different data sets that have the word Titanic, it was survived and sex in it, then we have to put data equals, like it just came up, and what's the name of this one? And all you do is need 3. See, I got a Titanic there that I was using before, so Titanic Survival, and then we're gonna hit the button. But look at that, what a coincidence. The values in this one must be 0, 1, 2, 3, 4, etc. So if we have survived, how do we change that? So the dependent variable has to be 0 or 1, and I'm going to explain to you why we have to keep it like we do. So that is what's 0 and what is 1. So basically, we're just going to quickly here recode the variables. But what's interesting, we get these on the Excel sheets. You could easily go into Excel as well and just say, no 0, yes 1. But here, I just want to show you a little thing, and we install a package. Let's see if I can spell it, Deep Liar package, which I believe that's it. And that seems to be it. So we're going to install that package. Now, notice what we're doing here, again, with all dichotomous and no linear continuous variables. This is going to use, opposed to what we talked about before with the OLS, the least squares that we talked about. We're going to be using the maximum likelihood estimate. That's because we're going to kind of make it, as statisticians would stress, into a linear model, but it's different. It's not going to be linear like we used with ice cream. The higher the temperature, the higher the consumption. There's a positive relation there. This, we are going to be comparing means. So we basically have, the likelihood of survival for a woman, and then we have the likelihood survival of a man. So this is completely different, but it basically works the same. Okay, so we have this. Let's see if we can do it. So we basically are going to look Titanic Survival, and notice money. Money is very important. Okay, so it's right there, survive. So take a look at that. That's what we use. And then what we're going to do is recode. See if I can get this well off. So you got the recode. I don't know. It's not coming up on the package. Why? Because we basically did not get it from the library. So let's hit this from the library. We got to go back. What is it? The DPL. Let's see if it's up. Yep. And then we have to get it literally out of the library. So here we are getting this out of the library. So let's go back up and see if we're able to do this. Is recode there? Let's take a look. Yes, got lucky. So what are we recoding? First, we're recoding this, copy and save. And this keeps the data as it is, meaning this isn't like we're not changing the name to Titanic Survival, and that is the $sign. So we're going to paste that in there, and then comma, and then what are we changing these to? So let's take yes. I'm sorry, let's go no first. Make it, what are we going to make it? 0. I'm going to explain why. Because we're going up. It's like no, and then 1 yes. And then yes. And let's make that 1. So what happens? We did it. So if you notice here, this has all changed to these numerical, basically dummy variables. We're just coding them 0 or 1. That's how the GLM will read it. You don't have to do it with the independent variable, which is going to be sex. So we're just going for survived. So let's go back up. As you remember, we can go back up and run it. So let's take a look. This is what we basically have. So we did get it and it did work. So let's take a look, you know, as you have to call it something and do the summary as we've been doing. So we're doing, oh, that's not the best way. Let me just go back up and do it like this. So let's take a look at how this is going to come out. So look at what we have here. We have the dependent variable survived, changed to these, it was dichotomous, yes or no. Nominal variables, not ordinal, not anything, just nominal with no order whatsoever, remember that. And the variable, the independent variable, sex, and then we're doing the family binomial. That is, excuse me, I'm dying, as I say in just about every video. Maybe I am. So we're basically doing the family binomial. That's the normal distribution. And there's a ton of families, but under time constraints, we're not going to get into that. So, and then the data, I put data Titanic Survival, what we're using. And the reason why is because I had another data set up with sex and survive Titanic. I was kind of fooling around with it. And let's take a look. So it did go through. So we're going to do summary. Take a look. And this is awesome. So what do we have here? So what we're going to focus mostly on is, of course, you see right down here, the p-value. That's going to be important, although not the end all. Some statisticians observe that we rely too much on the p-value, but there's a few things I want to show you. Obviously, you know, with the little e, the tenths, that this is very, very low, so it is statistically significant. And instead of the t, the student t, we have the z value, which is different because we have a ton of different, I think it's up to 30. They start changing it by default to the z value. There's a few characteristics of the Z value. One of them, most importantly, is that we have a larger number of cases that we're running. So as a result, it changes to the Z value. And then they think that we get closer to the actual standard deviant. So we know the mean and the standard deviant, but I'm a little incredulous about the central limit theorem there. So we can talk about that later. I've talked about that in class. With Alfred Landon, even if you got more cases, that is, in that case, it was survey data, they were still drawing upon the wealthy to get the survey data, and that's why they predicted Alfred Landon would win in a landslide against FDR, Franklin Delano Roosevelt, and that was a failure. That was a failure. So why? Because even if they increased the number of surveys they were getting, they still would have had the bias in their data. So I'm a little incredulous to say, oh, the more we have, the better, the central limit theorem, as you studied in the book. So I'm a little incredulous about that. But, you know, who am I? So I'm kidding. But I think that there is a lot of weaknesses with that. Okay, so what are we going to do here? We ran it. We have the Z value, not the T value, and it's still coming up. Very significant. But what's over here, we talked about a lot of these things. This is where we get why sex male and not female. We talked about this before. R does two defaults in this case to use the base. One, the number that comes first. So 0, if we coded the sex 0, 1, 0 would come first. And 2, in alphabetical order. And I changed that around in the last one. I think I put Z female. So A, B, C, D, E, F, right? Because my alphabet, I'm a little slow, as you people know. F becomes before male. So that is very, very important. So we have this. And now we want to see if there's any difference. So we see here, so what this is can be interpreted as that this is the log likelihood, which is different from probability. And I'm not going to get bogged down into this, but we're going to change it to the probability. We're basically seeing that you have the chances of a log likelihood of decrease by 2.4254. So you're basically getting a decrease of survival if you're male. So what would be the probability? I'm going to go over the probability and how to do it. I know it sounds like a pain, and a lot of people would say, you know, why does R or any statistical package make you do all this, which I'm going to show you, but it'll make sense. I want to get over a couple things. The null and residual deviance. Any kind of thing with residual, as we talked about before, is basically the lower, the better. And the null deviance is just the measure of the intercept without these independent variables. So there's one independent variable, so we add it, and then we get the residual deviance. And as you can see, it's 1,308, and then it goes down to 1,307. Why? The reason why, I really do think I'm dying of this thing. Excuse me, I feel terrible. But anyways, the point is that the residual deviance is with the independent variable, and you from the degree of freedoms, you're decreasing it by 1 because we only have one sex independent variable. But the point here is you want these as low as possible. And the difference between these two are important because if you get the same, or this residual deviance goes up, that's showing that there's not much difference when you don't have the independent variable. So that's like really bad. Now, I say that's really bad, but we're supposed to let the data fall where it is. You're not supposed to want necessarily a correlation or anything to be statistically significant, because if you do, you know, a lot of bias, you might fudge the data, etc. So you don't want that. So, I mean, but that's in the real world. In the real world, we want it to be just the data fall where it may. Now, what we're going to do here is figure it out. So the null deviance is 1741, and this is 1368. So it does decrease, obviously, using the p-value in this, and not by that much. And, you know, that is kind of worrisome because, you know, the lower the better, and this is high, but there is a gap between there, which is good. Now, a lot of people say, well, what's good and what's bad? It really depends on what you're running. I mean, I would say this is pretty good, particularly since we have a significantly low p-value. Way under 0.05, the standard p-value that's used in the social sciences. And the null deviance isn't that high, but then the residual deviance does go significantly, in my opinion, lower. So we could basically, we could say that there is a statistically significant difference between sex in whether you survived or not. See, chivalry will never die. The men must have allowed the women to get on the ship. See, one of the things is, if I were on the Titanic, I'm very egalitarian. I think every person for themselves. So I would have definitely jumped in and survived. But that's me. I mean, you know, I'm very egalitarian. I should be, you know, everyone's the same. So anyways, the point is, residual deviance you want as low as possible, but you also want the null deviance pretty low. But the gap between these, it is very, very important. And that's going to be important. Now, the Eicher scale is a little less important here because you have to compare it to other models of doing the same thing. The number of the Fisher scoring iterations, this is just the number of time in the algorithm that it took to come to its conclusion. And 4 is pretty low. So I'm thinking, you know, if you get a really high number, that can be like, at first I thought, is this the Fisher? Oh, wow. That, you know, it basically is saying that, you know, it didn't take long to come to these conclusions. And the ICA is pretty interesting because it basically compares to other models whether it's too complex. It reminds me of kind of how we did, how we saw that if we shoved in a bunch of other variables in the other one with the ice cream, it comes out even more significant, even though individually it's not significant. This is kind of similar where the ICA is going to tell you, compared to other models, that you want as few independent variables explaining the dependent variables as possible. We'd have to do more tests on this and other, I guess, shipwrecks, I don't know, but to see how this comes out. But what's important here is the p-value. We're using the z-value. We have the sex male, that's significant, a log likelihood, negative 0.4254, that man will die. Now, the log likelihood is not the probability, and that's what I'm going to do here. And again, null deviance as low as possible. The residuals, as we talked about, always want low because this is basically the variability of your data. So you don't want, again, to stress, you know, what do you want? If you know, I just prefer the data just to fall where it is. But, you know, people do kind of want their data to show a significance. So you'd want it as low as possible. And the residual deviance here is just, you know, this unexplained, how much, it's like, how good of a fit is this? And the lower is better because you want your model to explain the variability of whatever phenomena that you are testing. So in this case, we would want sex to be a significant variable on whether one died or not. And that is very important. And this is a new one to me that I really looked up. So I'm going to basically get this down from another paper, is that it's a little difficult, but you basically want your odds. You can do different things with this. So you basically could, for the odds, let's say we want it to be the odds and the probability. So I'm going to bring that up now that I wrote down, is this is basically your exponential. So we're going to change it. Let me put that in there. What number do we have? Now we're changing this. This is going to be the odds. You have to exponentiate this, and my vocabulary is definitely off. And then we're going to take the odds that we have here, and it's very interesting, and basically run it to be probability. So this creates your odds, the odds of being a male and not surviving. So this is what we're going to do. So what ends up with the prob? So this is all you got to do. There's a lot of stuff. So let me take a look. So it's 0.08. So that's your probability. You got an 8% chance of dying, basically, if you're a male relative to females. So that's how you get that. Excuse me. So you basically, I'm dying here. So you basically have that 8% chance more. So that's pretty high. Now, can we do anything else with this? Of course. So let's just start taking a look. We have passenger age. I'm not going to do because there's a titanic amount, no pun intended, of NAs. And R won't, it's good as a default NAs, R won't won't basically run it. So that's good. But because we're missing so many, it's like 72 or something, like really high, you're probably not going to get a good understanding of age. So there's an 8% likelihood of you dying if you're a male opposed to female. But let's do something else. Let's do, we'll call this M1. Now, look at this: survive, sex, family, binomial, Titanic, etc. Let's do the passenger. And again, I like this because all you got to do is really put in 3 and then passenger class. So you basically get that. Now, let's take a look at the summary. Now, let's summarize this. All right. So, I mean, that's pretty good. But look at this. The null deviance here it's not that it's necessarily high, but there's a not a big gap there. So, but it is coming up as statistically significant. What does that mean? Well, look at this. Each class now uses passenger class first because 1, remember, so passenger class is all the same in these, and then you have 1, which is going to be the base. So these are compared to the base, and then passenger class third. So first class, this is very interesting. Classes to back. Maybe Marx was right. Look at this. All right. If you're a left-leaning person, you're right. Class. We got to get rid of classes. Well, Bernie's out. So what are we going to do? Anyways, passenger class. The class is significant here, it says. So you basically were more likely to die. That is, you have a less likelihood to survive because it's going up 0, 1. Then if you're in the third class compared, and if you're in the second class, and these are compared to the base. So it's like interpreting that, you know, the log odds are higher to die if you're in third class compared to first class, 1.5567. For second class compared to the first class, it's 0.7, basically 77. So that's pretty good. I mean, very classist, and very significant here. But again, is this a good fit here? It does go down, and it's not as high. What's the one? Yeah, see, look at this. This goes down. This seems to be more fit better is sex, because even though they're both statistically significant, both models we just ran, this one looks a little different in the sense that 1713. This is 1716. So that residual deviance isn't going down much lower, and that's something that, you know, if you're going to publish a paper, you're going to do something. That's something that another person, or if you're in a peer review, would say was, well, your residual deviance isn't that low, and the gap isn't that big between the null deviance, and you want the residual deviance to be low as possible. And notice here again, the degrees of freedom, we have 1, 3, 0, 8, but because there's different dependent variables here, it goes down not 1, but 2. So the degrees of freedom are the independent variables plus the amount of cases we have. And it's decreasing because we have more dependent variables here, those 2, and the base is first class. So the class is very, very important here. And well, I don't know, as far as being statistically significant, it's important. For the null deviance and residual deviance, that doesn't look like it goes down that much. So a lot of people might say, well, this is measuring the goodness of fit, just like the other residuals when we talk about, you know, everything from the residuals in the LM function, as you remember, even the standard error, etc. We want those as low as possible. So again, 4 times for that. And that is how we do the logistical regression with the GLM function, but the GLM function only allows two dependent variables. Sorry, so survived, yes or no. The next one we have to move to is the multinomial. The multinomial, that's going to be in the next class. So the next lecture will focus on, and I swear I won't be dying. Well, maybe I will. Maybe I'll be dead. So the next one is going to be this. So this was a fun thing. I hope you enjoyed the Titanic. The Titanic data set I got from R. You can do this for fun as well. And you basically kind of understand these coefficients, the estimates. See, this is where I said the intercept is important in these cases more so than when we did linear. Here, because it was such a large case with over what, 1,308 cases. That's large. So you, again, that's why we're using the Z value opposed to T. But they're running the same, and they give us basically the C value gives us our p-value, which then we measure. There's 3 stars, as you know, since we've been running this in RStudio. And this is the null deviance. This is good. It goes all the way down to 1.3, whereas this one over here goes to 1.6. Because there's different variables here, you know, there's 3 in the class, first, second, and third. Does that affect that? I don't know. I'm not sure about that, but the point is that you want the residual deviance as low as possible to show that you have a good fit. Again, you know, a lot of people say, like, what's the best R squared? What's the best p-value? What's the best residuals? How low is good? I mean, that depends a lot on the field you're in. In engineering and others, like I mentioned before, obviously medicine, which is very important, they want a high R squared. That's not what we're doing here, but they want very low residuals. And it's a little high, but still, I would say it's statistically significant. But is it the best fit to use passenger class? Probably not the best. Not as good, obviously, here as sex. So really thanks for coming out, listening to me, even though I'm coughing. And look at this is, yeah, this is lower too. That's good. Meaning that we're explaining this data with just one variable. This is, I mean, sex seems to be the best bet here, but passenger class is also as the Marxist would predict. So if you're a Marxist or any kind of lefty out there, you don't have to be a Marxist to stress the role of class, but it looks like class is important here. And if you're in first class, you are more likely to survive. And I think that not much has changed since the Titanic. When did the Titanic sink? Like 1989 or something? So anyways, thanks for coming out. Leave any questions or comment in community forum, or just write me an email. Take care, everyone, and stay healthier than me.